Okay, yeah, as Matt said, we wanted to kind of talk about ZFS on Object Store. But before we do that, I kind of wanted to take us back in time, and I even wore like my oldest OpenZFS t-shirt that I could find back to 2005. So some of you may recall some things that went on with 2005, like Hurricane Katrina, the cancellation of the NHL season, the first flight of the Airbus A380. But there were actually other things that were more relevant to us, and that was ZFS was introduced into the open source community by the open Solaris project. And one of the things that, if anybody ever saw this presentation, it talked about really just kind of blowing away 20 years of obsolete assumptions. And so as part of this, I was like, hey, it's the 16th birthday of ZFS. Let's, we want to celebrate that. Let's go get some reaction from some ZFS developers and kind of see if they knew what was so exciting and what they felt about that. Oh, and sure enough, we actually had some that were really excited about the project back then. Today, things have changed quite a bit, but I wanted to talk a little bit about some things that we looked at when ZFS first came out and kind of what they really meant to file systems. So in particular, it addressed this brutal to manage problem that existed and still exists today with different file systems. But, for those that were doing system administration in those days before ZFS, you had to deal with the partitioning of volumes and kind of labeling them and modifying a bunch of Etsy files and dealing with inode limits and how big do I need to make things. And it was really just kind of problematic. And so it was a wonderful breakthrough when ZFS came out and said, hey, we're going to go tackle this problem and tackle it and solve it. In addition to that, it was kind of breaking some of the rules that people knew back then. We realized that the way we would make file systems bigger, we would actually create this shim layer with volumes, and we introduced this abstraction of a virtual disk. And so now we would have a volume manager that was involved, and it was another headache that we had to deal with. And of course, it had its share of problems. We would leave storage stranded. So if I had storage in this particular file system that I needed somewhere else, well, I couldn't move it very easily. It was just a pain. And then of course I had to still deal with partitioning and growing and shrinking, all of that stuff being done by hand. And so when ZFS came out and introduced the pooled storage model, it was great. It was just a breakthrough in the way that we were going to manage storage back then. It introduced the abstraction of the malloc free, where I just add storage to the pool and all my file systems get to use it, and it's wonderful. So I didn't have to do any of these, all these system administrative tasks just kind of went by the wayside. So it really was a game changer. But if we kind of look at 2005, there were a lot of things that back then that have really changed. YouTube, first video ever published, 2005. Apple was just switching to Intel. Git, just came out as an open source project. Netflix was shipping DVDs, and of course ZFS was released. It's also interesting, the largest hard drive in 2005 that was shipping was 500 gig. That's nothing now. So as we kind of look at how things have changed, we see that YouTube now gets over 300 hours of video per minute that get uploaded. Apple has switched their processors once again. Largest hard drives shipping, 18 terabytes, soon to be 20. Netflix now drives over 11% of all internet traffic is Netflix traffic. And ZFS has kind of proliferated and now is available on Windows, FreeBSD, Linux, and Illumos. What's interesting is that one thing you don't see here is what was going on with Amazon. Amazon was selling books and videos. And now they're a huge retailer, a cloud platform, and a video streaming service. And it's this cloud that has really changed the way data centers now look and how they've evolved. So again, let's look at kind of how things have changed. Back in the day when ZFS was coming out, we were talking about servers that were directly attached to storage. Then over the course of time, we started seeing these virtual machines getting propagated everywhere, and VMware using NAS and SAN as a way to distribute storage to all these virtual machines that were running now on our servers. And they introduced the concept of a virtual disk and having this abstraction layer where we now had like a VMDK that was really some kind of, block emulation storage under the covers. And the cloud has just done this and kind of like proliferated this in a much larger scale. Now we have virtual switches and virtual machines and, instance types, and storage still abound. And we have a lot of virtual disk abstraction layers. But it's changed the way we kind of deal with things today. It's made life significantly easier for most people. We now can do like on-demand infrastructure, which is wonderful. Like, as developers or system administrators or any company that needs compute on demand, being able to like issue an API call or click a button, and now all of a sudden you get a machine, an entire network set up, your own virtual private cloud configuration. And you only pay for what you need. So, I don't have to worry about going and buying a huge rack of storage. I just simply create some EBS volumes and I'm good to go. And if there's a service that I need, well, there's a whole catalog of managed services that I can put around it and just, leverage them. So I get like instant scalability and unlimited virtual block devices. But unfortunately, it's not all rainbows and unicorns. There still are problems. And the problems that we tried to solve back in 2005 have now shifted. So this virtual disk abstraction that we had with the volume layer, with the volume manager, has now been pushed down into like an EBS layer outside of the virtual machine. You still have the possibility of having stranded storage. I can't move things out of this EBS layer onto another virtual machine. I now have introduced capacity limits, which are things that we were trying to like get rid of. Now I have limited controllers and number of drives that I could put on a virtual machine. And what's interesting is like cost has been a big factor. The cloud allows me to pay as I go, but it also means that I don't want to overspend. So the way that I build up my virtual machine is I assign a small number of gigabytes to it, fill it up, and then I'll buy some more, fill it up, buy some more, fill it up, which leads to imbalanced space and potentially some performance issues. So as part of this project, we wanted to kind of like step back and say, kind of, is there a fresh perspective to solving some of these things that we had solved in 2005 and are now having to solve them again? And we thought to ourselves, what about object storage? So with cloud, object storage just proliferated. The abstraction of abstracting out your disks to these objects where you just have like a key and can get access to any object was kind of interesting. It was totally scalable. So unlimited capacity, all great things that, especially for a file system that was designed to be scalable and have unlimited capacity, seemed to be a perfect marriage. And it was cost effective. You didn't have to pay for the huge infrastructure that EBS volumes provided, because these weren't always NVMe drives that are sitting behind some storage controller. They might actually be like spinning metal. And it was a very simple API to connect to. And in a sense, this was another way of looking at pooled storage. What Object Store has done is it's just pooled all the drives together and exposing this through a very simple API and making it accessible to the application. So we thought, well, could you marry those two things together? Could we create this architecture again where you have pooled storage on top of object storage, which is a pooled drive concept, and reintroduce the malloc-free abstraction layer that ZFS was built on in 2005? This was great because it means with object store, it's like there's no disk to manage. I don't have to go and say, hey, S3, give me some more devices. I don't have to go shrink anything. I just simply remove objects and I'm only paying for the space that I'm using. So instead of having to go allocate, a 100 terabyte drive and putting 20 terabytes of storage in there and still paying for 100 terabytes, if I put 20 terabytes in S3, that's all I pay for. And I could scale as much as I needed. But if anybody's looked at Object Store or done any research around it, you'll often stumble across statements like this that simply say, Object Store is great, except don't use it for highly transactional and low latency types of applications. Because one thing that we know about object store is tons of bandwidth, but it's slow. So we wanted to look at that and say, okay, could we actually overcome this? Are there ways to overcome the latency concerns? We could provide a read cache layer. Well, ZFS already has an L2R component, so great, we could leverage that. We need a way to buffer writes so that we don't have to wait for the long latency when we actually issue a synchronous write. Hey, we have a solution for that too. We can put a slog in. And then lastly, we need to talk to S3. Well, there's an open source project called S3 Backer. Couldn't we leverage that? Uses Fuse, ties in, lets us go kind of directly back to the S3 device, and we can talk to object stores. So this seems like a pretty good model because it gives us all the components that we think are necessary to overcome latency. But there's some problems. S3 Backer, as wonderful as it is, has the limitation that it's every ZFS block is one object, which means that if I'm using large ZFS record sizes, great. I can take advantage of the bandwidth by sending 1 or 2 meg or 16 meg blocks. But if I'm doing something where I need 4K, 8K blocks, it's going to be expensive. L2ARC, for again, as good it is with working with SSDs, we needed something that could scale, and it has a pretty high penalty on its memory footprint. And Fuse itself has some issues. In addition, one of the things that we discovered is if you try to destroy a pool that's built in this model, those blocks remain on S3. So even though you think you destroyed the storage, you're still paying for it unless you go to the AWS console and remove all the objects manually. And in the end, it was just another virtual disk abstraction, which is again, not solving the problem. And then when we stepped back and looked at kind of our problem at Delphix, we want to be able to handle extensive random reads and writes. We're dealing with databases, which is one of the no-nos for using object store. So we needed to be able to have small blocks, in our case 8K, which are typically average, when compressed, are average around 3K. And we wanted to take advantage of the lower cost storage. Again, pay for only what you allocate. We also have customers that aren't system administrators. So the thing that was so wonderful about object store is that it's got a simple management layer. You don't have to worry about add additional storage, remove this storage, move this over here, rebalance that. Again, a lot of the principles that ZFS was built on, object store kind of mimics. And by having that simple management layer, that also meant that we wouldn't have these user errors that can often crop up. So people may have, you may have seen cases where somebody inadvertently removes the wrong VMDK, or they think that that VMDK is free and then end up using it somewhere else, and now you've corrupted it. We wanted to get rid of all those problems. So we needed to create something better. So for that, we set out on this architecture journey. We wanted to leverage the slog device because we felt that that would work really well, but we needed a better caching model. We needed something that could scale and scale to extensively large. So if we wanted to have 100 terabytes of cache, great. We need something that can do that with a very small footprint. And we needed to be very smart about its eviction, which means that it also had to be smart about the way it allocates blocks. We wanted to use large objects, but small blocks. So this one-to-one mapping that S3 Backer had couldn't work for us. We needed something better. We need to pack as many ZFS blocks as possible into one large object block and then ship that off. So this is what our architecture looks like. So the things that I'll call out here are the things that are in blue are components of ZFS that are effectively untouched. Things that are yellow are things that we had to modify, and things that are green are all new components. All the red components you see here are external hardware devices. So we're using a slog, so we still have access to an EBS volume, although because it's just for slog purposes, it doesn't have to be very big. So again, cost savings there. I don't have to go allocate 100 terabytes for a slog device. The communication to S3 is now being done by this userland agent, which we call the ZFS object agent. And it's actually talking objects to S3. but it's interfacing with the kernel through a new VDEV layer, a new VDEV component, I should say, which is the object store VDEV. So everything in the kernel still talks about ZFS blocks. And it's when we actually ship these blocks to the object agent that we actually are going to convert these into S3 objects. And then the ZFS, which is also a userland component, is also talking blocks. So we have the ability to like cache blocks, ship objects, and then the rest of ZFS kind of remains more or less untouched. So you may be asking yourself, why did we choose userland? Why didn't we just implement this in the kernel? Why did we put the object agent in userland? The biggest thing is we didn't want to go implement a bunch of HTTP and JSON parsing in the kernel. There's a lot of tools out there. We wanted to take advantage of that. We also wanted to kind of create fault isolation. So we built this agent that was able to restart, and it could crash, it could be upgraded, and it could change without impacting the rest of the system. So you can actually put in a brand new agent, restart it, and the rest of the kernel just picks up where it left off. And in addition to that, we wanted to take advantage of newer, richer languages that were available that aren't available in the kernel. And so we chose Rust. So then you're probably saying, well, why Rust? Well, the big thing here is Rust is fast. It's got a lot more semantics. It's much richer than a C programming language, and it gives us a lot of additional libraries that we can take advantage of. But the biggest feature is its safety net. So taking advantage of that has been huge for us, especially when you compare the number of lines of code that we've implemented in Rust versus C. And I show that on the bottom of the slide, where you can see we've had 1,700 lines of C code that we've introduced into the kernel, and also parts of userland, and then 13,000 lines of Rust code. But of those 1,700 lines, we've had to deal with data races, things in the IO pipeline, stalls, deadlocks, and they've taken us a long time to go solve. But we haven't had any of those issues in the userland Rust code. So it was a big benefit to us. But this talk isn't about Rust. I'm sure that there's a lot more features that are not covered here, and we have a lot of advocates that would be happy to tell you more about it. But instead, we want to talk about the design principles for the object store project. The biggest thing is the agent's independent. I mentioned that we wanted to have some fault isolation. So having the ability for it to die and restart was key for us, which also means that the kernel has to be able to resume and detect when the agent has died. So if you're in the middle of the transaction group, you need to be able to say, oh, I noticed that the agent didn't finish my, pushing out all my transactions. I can't assume what it knows or what it went out to do or how far it got. So I just need to push it all again. So it picks up and remembers where it left off. So in a way, it's kind of like, has this concept of communication is kind of out of band, that knows when to send data, what parts of data to send, where it needs to restart, and so forth. We also came up with a very simple block ID allocation scheme. Since we're actually just allocating and doing I++, that meant that we would never overwrite any given object. So when we allocate a block, we're never going to reuse that block ever again. This allowed us to make some very interesting things and simplify things like in-sync convergence. We now don't have to worry about multiple passes over the data, waiting to do things like don't compress during this pass, overwrite blocks during this pass. All that got simplified. We're able to simply say, we're going to allocate a block, we're going to ship it to the object agent. The object agent's going to put it into an object, and from that point forward, if we ever do another update on that, it just simply gets updated. We don't ever reuse the block. So the three big architectural components here are the object store in the VDEV layer, the Zeta object, and the Zeta cache. The VDEV object store is using a Unix domain socket to communicate from the kernel to userland. It's the one that's going to be responsible for taking offsets, which is what the rest of what ZFS uses, or DVAs, and convert that to block IDs, which is what the object agent wants to talk about. And it's in this layer where we do all our, our resume logic. So if we get a disconnect, we simply pick up and resume from there. It's worth noting that in this object store, there's a lot of room for improvement. So today we're copying the data from kernel to userland, but we recognize that we can make, share those pages, avoid the copy, and even change the data format that we're using. So at least at this point in time, we've kept it simple primarily to get this project off the ground. And the performance numbers actually look pretty good, and I'll talk about those a little bit later. As far as the Z object agent, it will then take these block IDs and convert them to object IDs. And Matt will talk a little bit more about kind of the details of how it does that. It's also totally responsible for all the object management. So it knows which objects are currently cached, which objects it needs to go fetch, how it maps from block ID to object ID, when it has to do consolidation, when it actually has to do freeze, and is responsible for all the S3 communication and authentication. And then the new Zcache is a simple implementation of an on-disk LRU cache. And this afternoon, there'll be a whole talk that describes the details of it. So with that, I'm going to turn it over to Matt to talk about the key data structures.
Thanks. All right. Yeah, so I wanted to talk about how we implemented this. What are the on-disk data structures, or maybe I should say on-object data structures, and what the implications are for performance of the project. All right. One thing that we could do is we could say every object in the object store is one ZFS block. So each block, ZFS takes it, let's say you have record size 4 meg, it compresses down to 1,234 kilobytes. We take that and we write that out into one object. We call it object ID 2. It contains block ID 2, and we put it in the object store using a key that looks like this. So everything goes under ZFS / and then this number is the pool GUID. So all the objects related to this pool will be under here. Data for data objects, and then object ID number 2. And then the next block that the kernel allocates, maybe it's bigger. We put it into a bigger object. Give it block ID, the next block ID 3, and the next object ID 3. Put it in there. So this is really simple. As long as your record size is pretty big, then this is going to probably work just fine, and you'll have performance that's kind of theoretically should be similar to S3 Backer. In practice, we saw it's actually quite a bit better. But obviously, it'd be a lot easier to manage than using S3 Backer because it's all native ZFS. The space is coming and going as you're doing those block allocations. So if all you care about is large blocks, then that's pretty much it. Like, talk's over, I'll go home. So why that caveat? Like, why does this only work for big blocks? Well, it's because we need to use big objects to get good performance. So this graph is showing us how throughput changes, maximum throughput changes as we increase the object size. And we want to be up here at, where basically this is the network throughput limit of about 25 gigabits. But the problem is that the object store is dominated by latency. So put object latency is around 50 milliseconds. That's kind of true regardless of object size up to some point, but it's at least 50 milliseconds. So in order to get good overall throughput, you need to either increase the object size, which is like moving to the right on this graph, or you need to have a larger queue depth, so have more put objects operations going on concurrently at the same time. So that's like switching from this red line, which is 100 puts concurrently, to this blue line, which is 1,000 puts concurrently. So we saw that kind of for the parameters that we cared about, around 1 megabyte makes sense as kind of a starting point. Maybe 2 megabytes would be a little bit better, depending on the queue depth. But the key thing here is that we want to be able to get good throughput when we're writing, and we don't want to have like a ridiculously large queue depth. I mean, 100 is already like pretty large. You run into limits like number of file descriptors that you can actually have open in a process. and other things that impact efficiency when going to really, really huge queue depths. All right, so that works fine as long as you have big objects, but sorry, as long as you have big blocks, you can just say one block per object. But what if you are storing databases and your database has an average of 3 kilobyte compressed block size? Then that's not going to work. 3 kilobyte object sizes would have very, very poor performance. So what we're going to do is combine a bunch of blocks into one big object. So in this example, we have like around 300 blocks being combined into one, roughly 1 megabyte object. And again, we're going to store it. We're going to have this concept of object ID. We're going to use that to generate the key that we use to store the object in the object store. But the mapping from object ID to block ID is less obvious here. So as we're writing, we're going to write out, the kernel is going to be sending us a bunch of blocks. It's going to be sending them in sequential block ID order. So first it gives us 123, 124, 125, etc. And the agent's going to be batching those up until we get about a megabyte of data, and then do a put object to store that into one large object. And the object contents are self-describing. So if we look at what's actually in this object, in the object store, it has the data and it also has a description of what the data is. So it says, I have block ID 123 and it's 3.5 kilobytes and it's at this offset within the object. Right, and the block IDs that we're talking about here are allocated sequentially and they're never reused. So once we've written block ID 124, the kernel's never going to come back and say, hey, change the contents of block ID 124. It's just always increasing for forever. So hopefully this, the right code path kind of makes sense here. You're just batching it together, splitting them all out. But what about reads? So if we want to do a read, the kernel is going to send up a request saying, please get the data for this block ID. And we need to figure out which object has that data inside of it. So the way that we do that is by keeping a mapping in memory that maps from the object ID to the minimum block ID. So we want this data structure to be really compact. So because the object IDs and block IDs are both sequential and increasing, if we get, say, for example, a read request for block ID 400, we can look through this table, do like a binary search and see that, okay, 400 falls between 346 and 667. So it must be in object ID 5. And we can go read that object ID and see that it has block ID 400. So there is obviously some memory cost to this. In kind of the current naive implementation, it's about 16 bytes of memory for each 1 megabit object, which comes out to, if you have 100 terabytes of data in your pool, in your storage pool, then it's about 1.5 gigabytes of RAM, which is maybe that's acceptable. I mean, 100 terabytes is, pretty big, at least for databases. But we think we can do a lot better than that because if you look at this table, you can see, the object IDs, we allocated 8 bytes for that, but really each one is just sequentially the next number. So maybe we can just get rid of that entirely. The block IDs, they're not sequential, but they can't differ by, 2 to the 64. Maybe they differ by, 2 to the 10 at most or something. So maybe we can get away with just 10 bits of information encoding the delta between each next entry here. So I think all things considered, we should be able to get this down to about a quarter of that, which is even more reasonable, 400 megs of RAM for each 100 terabytes. And of course, we need to keep this mapping on disk as well, or in the object store, I should say, persistently, so that if we crash, we're able to regenerate this in-memory table. And by crash, I mean if the object restarts. So it might not be a full system crash, but it might just be that the object process, the agent process is restarted. Then we need to read this back into memory. So how do we store the mapping on disk? Basically, we store it in a log. The log is just logically speaking, it's like an array of entries. The entries are going to tell us what's the object ID and what's the block ID associated with it, the minimum block ID. And this is going to be split into a bunch of objects. The objects are going to be numbered sequentially. So in this example, we have like chunk ID 0, which basically means like the object ID 0 of this particular object-based log. It'll be stored in the object store, again, with the key, something like ZFS / the pool GUID. Now we're in the object block map namespace, and then this is object 0 of that. And that'll contain maybe the first 10,000 entries and the next 10,000 entries in object ID 1. You know, what it comes down to is basically every transaction group, we're going to be appending a new object or maybe a couple objects to this log that indicates what other objects, what data objects were allocated and which blocks they contain. And then periodically we're going to have to, these objects might be kind of small, so you might end up with a lot of them. And so periodically we might want to condense these by rewriting this log more compactly in big, large objects. Similar idea to what we do with ZFS's space maps, if you're familiar with those. All right, so that kind of covers like what happens when we're writing, what happens when we're reading. There is one other operation that we might want to care about, which is freeing. So how do we reclaim space that's no longer needed? So there's a couple problems that come up when we think about this when you have a bunch of blocks within one object. So in this example, we have one object, object ID 4, and it has a bunch of blocks. And the kernel says, I'm going to free block ID 125. So what the free means is, it just means I promise that I'm never going to read this block ID again. And so FYI, you can do whatever you want with that. Preferably, maybe you use less data in the object store so that Amazon charges you less. So what we want to do is, in order to actually reclaim space from the object store, we're going to read this object and then write out a new version of the object that omits the block that we don't need anymore. So this works, and we're overwriting the object in place. So we're basically replacing its contents with the new contents. And because the object contents are self-describing, it's pretty cool that there's no race conditions here. So like if the reclaim is going on in the background and we don't have any locking and somebody else, some other thread is trying to read block ID 128, then they can do a get object. And if they get the old object contents or if they get the new object contents, it's going to work either way. So because the object is self-describing, whichever one they get will tell them where to find block ID 128 within the object. And that's fine. But it does cost us a lot of throughput. So to process this one free of 3 kilobytes, maybe, for example, we were doing a logical overwrite of some random block of our database file. And we wrote a new 3 kilobytes somewhere else, some new object, and we're freeing this old one because there wasn't a snapshot of it. So we wrote in order to write those 3 kilobytes, we had to write the 3 kilobytes of new data into some big new object, but then we also had to read a whole megabyte and then write almost another megabyte. So, you know, we're talking about 600x IO inflation with this naive implementation. So the solution to this is batching. So when the kernel says, I no longer need block ID 125, we say, that's great. I'm going to remember that, but not do anything about it right now. And I'm going to wait until hopefully we get a bunch of other frees of blocks that are also in the same object. And then I'm going to process those all at once. So maybe we get 200 out of the 300 blocks in this object are freed eventually. And now we can read this megabyte and then write out a smaller, about half a megabyte, less than half a megabyte. So we've improved the situation a lot. It's 170x better than the naive implementation on the previous slide, but there is still some IO inflation because we do have to read this and then write it out Even though it processes a lot of frees, there's still some cost associated with it. So the key to getting good performance out of this reclaim process is to make sure that when we're rewriting an object, it has lots of frees. So how do we find the objects that have lots of frees? Well, first of all, it would be nice if we could just wait a really long time for lots of frees to accumulate in all the objects. But we can do better than that by sorting the objects by how many free blocks are within them, and processing only the ones that have the most, only the best ones, the ones that have the most frees within them. And then we'll save the others for later, hoping that they accumulate more frees in the future. There's a bunch of like tunables here, and we can probably be smarter about this in the future. But right now there's like a tunable that says like, what's the, that basically tells us like, how long do we wait until we reclaim? And that's just like a percent of the total pool size. So we say like, hey, whatever your pool size is, having 10% of it free but not yet reclaimed is okay. Basically means like, you're going to be paying 10% more for your storage costs than if we were extremely aggressive about reclaiming the free space. But the trade-off is that the reclaim is much more efficient and uses less throughput. So how do we keep track of? We keep track of the blocks that have been freed but not yet reclaimed in this reclaim log, which is basically just an array of like, this is the block ID and this is the size. The sizes are used to go in to find the objects that have the most free space when we go to do the reclaim. So the reclaim log, as we're getting frees, we're appending to it. Then we need to load that reclaim log into memory in order to find which objects have the most free space. So that uses up some memory. Actually, we want to be able to have like as much outstanding frees as you want to set that tunable to without having an impact on the memory requirement. So what we actually do is we break up the reclaim log into several logs with different frees to different object IDs going to different logs, and that limits the amount of memory required to process the frees. So this example here is to load 10 million frees, but we can have we can have as many logs as we need so that no log has more than 10 million frees, for example, to limit the memory used. Limit the memory used to a constant regardless of the pool size and the amount of outstanding reclaimable space. All right, so there's a couple more problems. First off, the object block map memory usage is going to keep growing and growing over time. So as we're doing writes, we're allocating new objects, we're appending new things to the object to block mapping, we're keeping track of those in memory in the table that looks like this. And the issue is that if you're just writing and you're not really freeing much, then it's not a big deal. But if you have a lot of churn, like say because you have a database and the database is like randomly overwriting lots of different blocks in the database files all the time and like writing its logs and then overwriting its logs at the database level, then you're gonna have a lot of churn, meaning like a lot of the data that's present in the pool now won't be present in the pool, a month from now, but it'll be replaced by new data. So the size of the total amount of data in the storage pool might remain relatively constant or be growing slowly, but the total amount of data ever written into the pool is very, very large. So for example, if you're writing at 100 megabytes per second on average, then this table might grow to be like 12 gigabytes of memory for every year that you've been running this pool. And we have customers that are writing at this rate, at this average rate, with our block-based solution, and that have pools that are many years old. So that seems like not a great use of memory. And the other problem is that the objects are going to get small. So as we rewrite each object, omitting the freed blocks, it's going to get smaller, and then maybe we do that again and again until it's like very small. And that means that if we need to like do a table scan or read through a whole file, getting all of its blocks. Now we have to read a whole lot of small objects, which has the same problem as large objects to a little bit lesser degree. It's also latency dominated. The latency is kind of at least 20 milliseconds. So that's less than half of the puts, but it's still pretty significant. And again, you want to be using large objects to get very good throughput with reasonable queue depths. How do we address that problem? We address it with object consolidation. So when we're processing, when we're doing reclaim and processing freeze, we're going to look at several adjacent objects and the freeze that are associated with all of them. And we might see, okay, in object ID 4, we're freeing most of it. The yellow blocks are the ones that are being freed, and the blue blocks are the ones that we need to retain. But maybe, there's only a few of them. Those don't add up to a megabyte. They add up to like some small fraction of a megabyte. So let's look at the next sequential object ID, so object ID 5, and see what needs to be freed there. Okay, a bunch is being freed. We need to retain a little bit here. Let's add those to this object. And as long as it's not a megabyte yet, we keep on doing that, accumulating more and more, consolidating the retained blocks from more and more objects into this one object that's going to replace them all. So to do this, we can kind of figure out all of this based on the in-memory metadata without having to read any of the data objects. And then we need to read, all three of these data objects, and then write just the one new large one, and then eventually delete these object IDs 4 and 5 that are no longer needed at all. Or sorry, object IDs 5 and 6 that are no longer needed. After we've persisted the object to block mapping change. So in the object to block mapping, we're going to remove the entries for object IDs 5 and 6. In the on-disk log, we're going to add a free type entry saying that these are no longer needed, and then we're going to remove them from the in-memory table. So now, there'll be some object ID 7. You'll have an entry for object 4 and object 7, and then we know that all of the blocks between them are in object 4 because 5 and 6 aren't there. Cool. So this works pretty well. There's a lot of work that we can still do in the future to improve this even further. So like one of the ideas is right now we're kind of batch processing the reclaim. So it's like we start reclaim, we do it as fast as possible. We stop doing the reclaim, we wait until you hit the high water mark and then do it again. We could probably improve on the behavior of that by chipping away at it like every transaction group little by little, and then having like some kind of feedback mechanism that tells us like how fast we need to be chipping away based on how close you are to getting to the high water mark. You might also want to have different kind of controls over like when this happens. If it's impacting performance, you might want to only do it at night or on the weekends. You might want to have some like minimum efficiency setting where you're like, yeah, I don't really mind paying for that extra storage space for a while, but I really don't want to impact my network throughput by doing lots of gets and puts. So, I want to say like only do it when you're able to free like 90% of an object or something like that. But, absent those future performance, how does it actually work today? So this is a graph showing the x-axis. The x-axis is time. This is about 30 seconds here. And the y-axis is well, the green, red, and blue are network throughput, and then the magenta here is amount of space that's allocated in the storage pool. So what's happening is we're going along. TX2 sync is putting data to the object store at about 700 megabytes per second. Then we start a reclaim, and then we're going to be reading and writing data. We can do that very quickly. And then we go back to that's done, and we reduce the amount of allocated space. So the workload here is random writes, about 15,000 IOPS into a 1 terabyte file, completely random locations with record size 8K, and the average compressed block size is 3K. So this is what I would consider a very demanding test. The only way that might make it more demanding would be to increase the file size, which serves to scatter the writes even further, and the indirect block updates become even more expensive. So on this very demanding workload, we're seeing that we're still able to process freeze at about 1400 megabytes per second, versus the writes are about 700 megabytes per second. So it kind of makes sense that like half the time we're reclaiming and half the time we don't need to be reclaiming. For our workload, which is this pretty demanding workload, because we aren't reclaiming all the time, we're able to keep up, and we can see that the impact on the rate that we're ingesting data with TXT sync writes, it goes down a little bit, but not that substantially while we're in the middle of the reclaim. So the kind of conclusion for us was there's spare network bandwidth, and we're able to do this in parallel with ingesting the writes, still at a good throughput. So even despite not having some of that future work, it looks like it's good enough for our workloads. And for more typical workloads where you're like, the record size is the default, and most of my data is in large files, and they have the record size of 128K or maybe even more. Mostly what I'm doing is accessing files sequentially. Really, this solution is vastly over-engineered for that kind of use case, and the impact of reclaim is going to be negligible on that kind of use case. But we wanted to make this work for our use case, and it's also really satisfying that this works for a wide variety of use cases. We don't have to say like ZFS on object store, as long as you're just using it for archival or backup or whatever. This is really it's usable for general purpose workloads, even including some of the most demanding ones. Obviously, there's performance concerns there, but the ultimate, the bottom line is that the performance is very good. All right.
Okay, so as you've been told, the ZFS object agent is a userland thing. So we'll start by kicking it off, and we'll let it run on that window. So we are invoking the ZFS object agent, and off it goes. And now we are ready to create a Z pool. So as you might imagine, we have to specify additional parameters so that we can specify where the pool is going to be created. So we need to specify the endpoint and the region where the S3 bucket is going to be, the pool name, obviously. And we have, as George mentioned, we have a new VDub type, the S3 type, and we have to specify the bucket, the place where all the objects will reside. And in this case, I'm going to add in a log device as well. And so the pool is going to get created. And so that's the pool for you. And if you notice, just like the device is specified, the bucket is specified here. And you can see the NVMe log device there as well. So I started off the agent by hand, but you probably want to be using some system management service like systemd to run this. So let me pause the video just a second again. So as George and Matt mentioned, the agent is designed such that it can be killed and restarted, or it can crash and come back up and things are still going to be fine. So it's resilient. So that's exactly what I'm doing here. I'm killing off the agent. The pool is still online, and I'm going to start it off as a systemd service. So the systemd service is on, is going, and let's take a look at the log on this window, the debug logs, while we proceed with the demo. All right. So now the agent is running as a service, which means it will get auto restarted in case something goes wrong. So Matt talked about workloads where you have 8K record size, compression is turned on, and you have a large file and you do random writes. Let's do just the same thing. Okay, let's create a large file, and we have a ZFS file system with 8K record size, compression turned on, and let's go do some random writes. So we're going to first create a large file, and I'm going to speed this up. All right, and next, let's do some random writes. And then we are going to use IOStat to see how it looks. And IOStat has been improved or enhanced with the -o option so that all object stories things are listed. So if you look at the first column, that's the traffic between the kernel and the agent. The second column tells you about the traffic between the agent and S3, the object store. The metadata traffic is captured, and reclaim happens. Matt went over that quite a bit. So reclaim happens as well. So the thing to notice here is that we are doing about 100 meg of throughput, and the throughput between the agent and the S3 is also roughly close. But the number of objects, the operations, there is a significant difference, about 100, 150 operations from the agent to the S3 bucket, but about 36K of operations is what the kernel is doing. You also notice that the reclamation, the object reclamation is also going on, and it goes in bursts, and we keep reclaiming objects. All right, let's kill that workload and let's look at something else. So import export. Now export is fairly straightforward. You export a pool and you're done. Nothing special about this. But import, as you might imagine, like zpool create, it needs additional parameters. It needs to be told where to go import stuff from the endpoint, the region, and the bucket, the S3 bucket. So the -d option specifies the bucket. Think of it's similar to the -d option for block-based devices, where you specify a directory to go look into. That's the bucket equivalent. You specify the region, the endpoint, and then the pool name, and zpool imports it for you. It takes a little bit of time. We'll talk about that in a bit. About 5 seconds, and we should be done. So we are done. Let's take a look at the zpool list. So pool 1 should be there. Yeah, it's there. And we can also do a search import where you tell ZFS import to go look for pools. And so let's try that on our bucket. And interestingly, we have a pool that we did not create on this VM, pool 2. So why don't we just go try doing a zpool import on that? Pool 2, let's go try and import that. And we hit a failure. Specifically, it says that the pool can't be imported because it's currently hosted on a different host. It's imported on a different host. What exactly happened here? Hey, Paul, can you walk us through this?
Sure thing. So this is an example of a feature called Multimodifier Protection, or MMP. ZFS already has this feature implemented in the kernel. It's useful for situations where you have storage area networks or network attached storage, where multiple systems could potentially try to import the pool at the same time. We re-implemented this in the agent for a very important reason, and that's that it's extremely simple in the cloud and object storage use case for multiple systems to be accessing the same bucket, to be accessing pools within that bucket. And with some pretty easy misconfiguration steps, it's very simple to have multiple systems try to import the same pool at the same time. ZFS is an extremely reliable file system, but multiple people trying to write to a pool at the same time is a very fast way to data loss. So for that reason, we decided to re-implement MMP in the agent. protecting both the ZFS data and the agent's own metadata. The checks take slightly longer. As Manoj pointed out, during the import process, it takes anywhere between 5 seconds and 20 seconds in a contended use case. But it's designed in such a way that it is almost impossible for multiple systems to end up succeeding at an import. It would require very extreme networking configurations on multiple systems happening at exactly the same time. And so the additional time cost was deemed worth it, given how important it is in the cloud use case to prevent multiple systems from accessing the data at the same time.
All right, thanks, Paul. So let's do a little more of the MMP stuff. Let's go over to the host where the pool 2 is online. Yeah, it's right there. And instead of cleanly exporting it and importing it on the other pool, let's do something more interesting. Let's just power off this this other VM, and we power it off, and then we are going to see if we can import it safely with MMP on the other VM. So let's try that again. But this time it's going to take a little longer because, as Paul said, it takes a little longer for the negotiation to happen. And I'm going to speed this up. All right, it took us about 34 seconds here, but the pool has been safely imported and it's online. So let me pause the video again to talk about something else. If you noticed, we had multiple pools on the same bucket, and that's part of the design. That's very much how we wanted this to be. The bucket is can be shared by multiple pools across multiple hosts, and each pool has its own namespace into which all the objects go. So they don't clobber each other, and you could have a shared bucket, or you could have different buckets if that's the configuration that you want. But shared buckets are totally okay. So if you look at the status, yeah, they are both on the same bucket. Pool 1 is there, pool 2 is also on the same bucket. Okay, so next up, let's take a look at some of the zpool properties. We have a new object endpoint property, the region, the credentials profile. We'll talk about that in just a bit. And so those are the new properties that an object store based zpool has. Next, let's talk about zpool destroy. Zpool destroy for object store based zpools are slightly different. Different because we or the customer is paying for these S3 objects, and unlike a block-based zpool where you destroy it, the blocks stay there. It's marked as destroyed, but the blocks just stay there. We don't want that behavior for object store. When we say destroy, we want the objects to go away so that we are not consuming space on S3, right? So when you destroy a pool, what happens is the agent kicks off a background task that goes and cleans up all the objects, destroys them, and reclaims the space. So zpool status, while the pool is being destroyed, will tell you that it will list the pools that are destroyed. And once the pool has been completely destroyed, you have an additional flag, the -- destroyed option, that can give you a list of pools that have been destroyed, so that you can confirm that your pool has indeed been destroyed. And if you don't want to see that anymore, you can use the -- clear and it'll go away. Now, I very cleverly did not deal with credentials so far, and let's now talk about that. So if you have used the AWS CLI, then they take as credential sources, they can take credentials from a variety of sources. And for this demo, I used the AWS identity and access management roles that are associated with an instance profile. And that means that, or what that gives you is that you don't have to deal with credential rotation and things like that. It's done for you. You could do that. and all the various sources that the AWS CLI takes as input, the ZFS object agent can as well. So you can use instance profile if you like, or you can use environment variables, AWS credentials in environment variables if that's your preference, or you can specify it in the .aws credentials file. You can also have multiple of these credentials as profiles, so that in case you want to have pools, different pools on different buckets with different credentials, you could do that as well. So here is an example of how you would do that. Fake credentials, but you have profile 1 with one set of credentials, profile 2 with another set, and you could use a third one, which is the EC2 instance metadata. And that's all I had. Thanks.
So what I wanted to talk about now is a little bit about performance. So when we, I mentioned before that we actually started off kind of looking at like S3 Backer and L2ARC and some of the existing components. So it made sense for us to kind of see where do those things stand today. So like we ran some tests, some performance numbers just using S3 Backer and trying to get like its raw throughput. So what you see here is the raw throughput of sequential reads and sequential writes. And I'm using FIO and the ZFS perf test to actually generate these numbers. So this is using 128K IO block size. So I'm going relatively large, but not as big as maybe we would necessarily need. But what's interesting is it gives us a baseline. So then we wanted to see like, where do we stand with our current implementation of object store on ZFS? You can see that we're right around the 3 to like 6x range of performance numbers. So we're getting a lot more read throughput and a lot more write throughput. But that's great because like S3 has a lot of throughput to give, and you're going to be limited by how much bandwidth your instance type has. But what we really care about are what are the IOPS? So again, I wanted to start off with like S3 Backer and kind of what does that give us in kind of the configuration that we had. And I started off without an L2ARC. So this is just going straight to the S3 device. You can see that the random reads are just kind of horrible. And random writes are all right. But nonetheless, this would not be something that would satisfy us. And the latency for S3 Backer is actually really bad when we talk about reads. So we needed to kind of look at like, this was kind of a non-starter for us. Again, looking at the comparison with just using ZFS and our implementation of object store, we see that at least in this case, we're able to lower the latency of random reads from 346 milliseconds to 89 milliseconds. So still not great, but a big improvement overall on kind of where we're headed. So we kind of knew we were on the right trajectory. So what if we added an L2ARC device? And again, comparing both S3 Backer and ZFS with an L2ARC, the good news here is that we're actually now getting latencies in a more acceptable range. And I mark it here as yellow. So 17 milliseconds for random reads. Okay, it's probably like, comparable to like, maybe some older spinning disks, but not necessarily what you would need for like high transaction rates. So this was kind of like our starting point. And again, our starting point was really based off of, taking ZFS and making a more integrated solution to talk to the object store. But as I mentioned in the talk, like we needed something better. And that's where Zcash is going to pick up. So we'll talk more about that this afternoon. But is there more to like what we've solved here? Like as you start thinking about kind of some of the techniques that we use to implement object store, can we go beyond that? So I wanted to kind of like throw out some kind of crazy ideas of like, where do we go? Can this be leveraged in other ways? For example, could we use this for shingle media? Could we define an object to now like define a track on a shingled media drive and then use some of the techniques of like actually knowing a block to object mapping to define and move regions around when you're actually going to do writes? Maybe this replaces the need for BP rewrite. We've talked about that for many years. Could we abstract the block pointer? Now we have the ability of having the block pointer just be more, virtualized. And it doesn't matter where its location is, because again, using the object map, could we actually determine where its new location should be if we need to move things around? And there's many more. There's many things that you could think of. The other thing to think about here is, what would you do with ZFS if you had unlimited storage? What if you could store anything on here and not have to worry about those capacity limits? I think that's the era that we're kind of going into, and that's what makes this a really interesting thing for us. And hopefully it sparks some ideas in the community. And with that, we thank you, and we'll open it up to questions.
All right. So there's a question about Scrub, and then a couple of kind of related questions about Scrub and how does zpool status-v work. At a high level, I mean, ZFS is still maintaining a checksum of each data block stored in the block pointer in the indirect blocks. And so you can run zpool scrub. It'll go read every data block off of the object store and verify that the checksums match. And if they don't match, then it'll be reported in the zpool status-v, just like normal. Right now, the performance of that is not great because we don't have the sequential scrub optimization hooked up. It needs to be updated to know about block IDs versus VDEVs and offsets, because we've kind of shoehorned the idea of the block ID into the block pointer, but a naive interpretation of the block pointer that doesn't know about that would think that there's overlapping allocations. So we need to teach that code about the block ID stuff. But otherwise, works naturally. And
yeah, it might be worth mentioning, Matt, too, that although we didn't talk about it here with Zetacache, is we have taught Scrub to know about Zetacache,
yeah,
and have the capability of scrubbing the blocks that are going to be stored on the cache. For those that are kind of familiar with the way the cache normally plumbs into the rest of the stack, it's this is it's living below the IO pipeline. So it's in a different location, which meant that we had to kind of treat it a little bit differently, but it actually worked out really nicely for us.
Yeah, I think that's a great point. It does integrate with the Zetacache that we'll hear about this afternoon. There are a couple of questions that haven't been answered yet here. So from Thomas Wagner, are there any active use cases for S3 already? I assume you mean anybody using ZFS on object store on S3? We haven't put this into production yet. We're still working on implementing it. But the use case is the one that we've described of storing databases in our Delphix data virtualization product.
Yeah, the one use case that I found very commonly when we kind of were getting started is there are a lot of people that are using the S3 backer implementation. I found people both on Linux and FreeBSD that have been using this, and they're using it primarily for backups, right? Because as I mentioned, any of the literature you read, object store is just not really designed for for low latency, high transaction type applications. And so the applications that are out there are not pushing that limit. We're kind of venturing in that. And from what we've been able to find and the performance numbers we're getting, we feel that this should open up a lot more use cases if we can get to that kind of low latency, high transaction rate.
Cool. The next question from Powell is asking, what happens if you allocate an object in S3, but then the system crashes, or maybe the agent crashes? Is the object leaked, or do we somehow figure out how to delete it? Yeah, that's a great question. So you can imagine something here where we're writing out these data objects, we're doing a TXG. So first let's cover the case of the system crashes. So let's say we're in the middle of a TXG, we've written out object A's 5 and 6, those are part of the next TXG. The whole system crashes, the kernel crashes, we come back up, we open the storage pool. How do we find objects 5 and 6 to delete them? We do. So we do find them and delete them. And the way that we do that is, so I simplified the key here a little bit. We've actually forward padded each of these object IDs with like it's actually, you know, 00000000005. And the reason is that then it lets us easily find, we know what is the last valid object ID that's basically stored like in the equivalent of the Uber block, like in a per TXT data structure. So when we open the pool, we're like, okay, the last valid TXT is 192. In that TXT, the last valid object ID is 4. And so we can do a list objects and list all the objects that are in this prefix after the one that's 0000004, and that list will contain, you know, 5 and 6, and then we'll delete them. So that's actually a very quick and efficient way to take care of that. There's actually a much more interesting and tricky case where you're in the middle of a TXT, the agent crashes or is exited and restarted, and then you need to pick up where you left off in that TXT. So we've written some objects. The kernel doesn't know about that because it doesn't know about objects at all. It's still running, but it doesn't know about it. The agent has been restarted, so it doesn't know about them. So in that case, what we do is we do the same thing of like, okay, the last TXT that I wrote out has the last object ID 4. Let me list what objects are after it. But those objects, we don't necessarily delete them because we might be in the middle of writing them as part of this TXT. And we may have already told the kernel that all the writes to those have completed because like it was persisted on disk, it persisted into the object store. And as far as the agent was concerned, like everything was done and it told the kernel, great, those writes are done. You don't need to hold on to that memory anymore. And so the kernel's like, great, like I freed that memory. The kernel doesn't have any way to replay those because they aren't in flight anymore from its point of view. So, but then there might be other outstanding writes from the kernel's point of view that do need to be replayed. So basically we have to stitch together what was left on disk, like what objects are there, and the outstanding, the ZIO writes that were outstanding when the agent crashed, which the kernel can replay into the agent, and then we can stitch that together and fill in, you know, any missing objects that hadn't been persisted.
Can you hear me now?
Yes.
Perfect. First of all, awesome talk, awesome functionality, which I was waiting for since the leadership meeting it was introduced on. And on that leadership meeting, I shared my use case for that, and that would be ability to mount to import pool on multiple hosts and mount data sets on those multiple hosts. And I have a volume migration of containers in mind for that. I know that writing to the same pool on multiple hosts, as was said on the presentation, is questionable. But can we imagine a situation when hosts are allocating specific data sets and block the access to specific data set? And when it was unmounted, it is allowed to move on to the another host. Right now, for the containers that have less demanding workload, I'm using ZFS Fuse implementation that allows this quick switching between hosts. For the more demanding containers, we have ZFS send receive and the classic data set on the each host. But switching those workloads is challenging in matters of time that is used to send and receive said data set.
So one question, Marcin. So in the case where you're using it, are you kind of envisioning like moving the storage pool to another host, or how are you you're replicating the data completely?
I have in mind the one storage pool imported on multiple hosts and data set that are dedicated for each host.
Yeah, so effectively you want a kind of like an active type of high
Yes.
availability type of
Yes, but with exclusivity on the dataset level.
yeah.
Yeah, I think that's, I mean, that's a neat idea. It doesn't fit exactly into what we've done here. I mean, because there's still pool-wide metadata that, you know, all of the hosts would need to access and update. Like, for example, the last block ID that was allocated, right? So maybe during the hackathon or the discussion afterwards, we can see, bounce some ideas around of like what could be done there. But I don't think that it's like, it doesn't just work, that's for sure.
Right.
Okay. Second question. Have you in mind optimization for the use case when we have our own implementation of S3, let's say min IO, when there is no impact on the amount of the API calls you are allowed to use?
We got a related question on YouTube actually, which is, do we have any tunables around controlling API calls to limit costs for the services that provide that?
Yeah, we haven't thought extensively about like what exactly you would want to optimize differently. We do have extensive tunables to control all this stuff. So like average block size, average object size, you know, the reclaiming, how all that stuff works. So hopefully, you know, the fact that S3 is like more restrictive in terms of like you have to pay for every little thing means that it'll work fine, you know, and we, you know, kind of try to make it work well in that environment. It should work well in less restrictive environments as well. If there's some other cloud provider that like charges you for something that Amazon doesn't charge you for, then that would be interesting to know about so that we could think about, you know, how you know, what costs might be incurred there given the design.
Yeah, and definitely with like MinIO, I mean, we've tried that out. It works just fine. But yeah, there might be cases where we could make a different design decision, knowing that we don't have to pay, you know, the per egress, ingress, you know, operation type costs. Yeah, that's something to definitely like, you know, think about.
Yeah, and then a related question that we also got on YouTube was a number of people were asking about stuff at the VDEV object store layer. You know, do we support clouds other than S3? Would it be possible to have multiple clouds backing a pool in like a mirroring configuration? And is it possible to have disks combined with object storage as the backend? And I answered all those there, but I figured I'd just repeat the answers here. Right now, we support any cloud that provides the S3 object storage API, which is a number of them. But we do plan to add support for more things in the future, like Azure, I think, has their own API, and we would like to add support for that as well. Currently, there's no capability to mirror between multiple object stores as the backend, but again, it's not precluded at all by the design. It's just something we would need to actually like work on and implement. And then the question around having disks combined with object storage and like possibly as a tiering solution is an interesting idea, like having disks as your primary store and then migrating data back to object store to save space and stuff like that. We haven't done any design work on it, but it is definitely something that would be interesting to work on in the future, I think.
Stay tuned for the Zetacache talk.
Yeah, it's kind of related to that.
Yeah.
I mean, we you know, we kind of need multiple tiers, but we design it as a cache rather than a tiered kind of thing where tiering usually means that the data might live in exactly one place and you can like move it from here to there and it doesn't exist here anymore, which we didn't see as a requirement for our use cases. Caching is good enough. There are a couple other questions on the text that I think are interesting. I'll repeat. From YouTube, Rahul asked, how does reclaim happen if you're using like S3 tiering or lifecycle policies? So the free space reclaiming that we're doing doesn't interact with those S3 level things. Basically, like we're kind of assuming that only one copy of an object is retained in terms of life, in terms of like if you're using S3 like life cycle, like keeping old versions of it, versioning. We don't take advantage of that versioning, and we kind of assume that you don't have it. You could probably use that to like roll back your pool really far or something, but we haven't tested that out. In terms of tiering, the tiering, I mean, it's going to kind of just work and do what it does, like moving stuff from the S3 like normal tier to Glacier or whatever. Of course, if we go and do reclaim and that like needs to read some old object, then that's going to bring it back from the Glacier tier to the main tier. So you would probably want to configure like the reclaim and the like movement policies such that like normally stuff wouldn't get moved into the Glacier tier until like most of the freeze had already been processed. I suspect that it'll kind of like if you have those kind of workloads that for which the tiering is useful, then it'll probably just work fine anyways, because you're probably using big files and big blocks, and the reclaim is really not an issue in those cases. In theory, I think we probably could add some smarts to say like, before doing, you have different reclaim policies for stuff that's in the Glacier tier versus in the normal tier, and like we can query and find out, oh, has this object already been moved to Glacier? If so, then let's not bother reclaiming it maybe at all, or not until it's like 99.9% free or something like that. That would be an interesting extension. Jorgen, do you want to ask your question live?
I suppose I could. I don't really know much about S3, so I don't know if there's a particular limit to it, but all your examples you had, the key count IDs counting, I mean, your example there is 4, 5, and 6.
Yeah.
And then you have the object mapping to take the block number and a map into which ID goes to that table. Is there any particular reason you couldn't, instead of using 4, 5, and 6, use 1, 2, and 3, 3, 4, 5, 3, 4, 6, and so on?
Yeah, like
the lowest block.
Why not just use the object ID equals 123, right?
Can you not list what you have, perhaps?
I mean, you can. I think that a solution along those lines, we considered that. I'm trying to remember all the shortfalls. So essentially what you're saying is like, take this table, but get rid of the object ID column, and then just have the min block ID and use that as the key.
Essentially, yeah. Saving the memory and so
on. I think that might work until you do object consolidation.
Yeah, it does fall apart then.
Because let's see.
It should work for consolidation as long as you always consolidate to the left. Yeah.
Yeah, since we're always consolidating to the left, it might work.
Yeah, it's an interesting idea. I mean,
it makes finding the orphaned objects after you do a reboot. You have to, I mean, you're not just going like, iterate through the next objects. You have to like scan upwards, but it should still be pretty doable. I don't think that should.
I actually had the design that way in an earlier version. And now I'm trying to remember, like, I'll have to go look through my notes and see why I changed it. It might be that I just changed it for ease of comprehension. Because like, it's a little bit hard, it's like hard to wrap your head around, like, oh, there's like this object whose ID is, 346. And that tells me something about the contents of it versus this more abstract, more cleanly abstracted layering. But yeah, we should go look at that again and see if there's a memory savings that we could have by doing that.
Okay, thank you.
Did you have another question that you wanted to ask?
Not me.
Okay.
There was one other question from YouTube, which was about the MMP stuff, which is, would it be possible to have one modifier and also have readers operating in parallel with the modifier? And the answer to that is Yes, except that once blocks start to get reclaimed, you can run into some issues. So you could potentially use something like checkpoints for that, which would prevent the reclaims from happening and should make it possible to do reads of things like snapshots safely, even if the active system could be destroying those snapshots or whatever. And checkpointing is implemented for the object store as well. We do have that working.
Yeah, the behavior would be like at one level kind of similar to having a block-based pool that has one writer and multiple readers, where it's like, yeah, like as long as the reader starts from a given snapshot from a given TXG, and those blocks aren't freed or overwritten, then it'll continue to work. And you could use checkpoints to ensure that that's the case, where you say like, okay, like multiple readers open the pool from the checkpoint, that's totally safe. But if you want a more like arbitrary thing, then you might get checksum errors or on critical metadata, and things might blow up. For object store, it's kind of similar, but it's a little bit safer because you aren't going to get like checksum errors on weird things. The only error that's really possible is like I'm doing a read, the block should be in this object, but it's either not in that object or the object ID doesn't exist anymore. So it should be like a little bit easier to handle that error maybe. But you would still have that problem in the kind of general case if you weren't using the checkpoint like Paul was saying.